Good afternoon, class. We are looking at Chapter 1, Functions. Here's Section 1.7, Inverse Functions. So in this section 1.7, Inverse Functions, the objectives are verify inverse functions, determine the domain and range of an inverse function, and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse on the same axis. All right. Let's recall what we looked at: composition of functions, algebra of functions and their domains. We have f plus g, f minus g, f times g, and f over g of x, and they're simply following the same algebraic technique of the four operations. In the last case, g can't be zero. When we look at this graph, we should recognize if you have 2 points of a graph connected, it creates a line known as a secant line. And as long as you have 2 pairs, you can calculate the slope. Whether you use f of b minus f of a over b minus a, or f of x minus f of a over x minus a by calling this x, or f of a plus h minus f of a over h by letting this be a and this distance h, they all refer to the same thing. If the domain of f of x is a and the domain of g of x is b in this case, the domain of all of these functions is a intersection b, because both f and g have to be defined. However, the very last one, not only it's the intersection, the restriction g of x can't be zero must be followed as well. So we are going to say x is an element of a intersection b such that g of x is not equal to zero. And for a simple reason, we can't divide by zero. In the case of a composition function, f o g x is the domain of g, g of x is the domain of f of x, we get f o g of x. So f o g of x is f of g of x, g of f of x is g of f of x. They are not necessarily the same unless they are inverse functions. G of x must be defined, so any x not in the domain of f must be excluded. F of g of x must be defined, so any x for which g of x is not in the domain of f must be excluded. Also, we looked at absolute value equations and inequalities. Recall absolute value of x is x if x is greater than or equal to 0, minus x if x is less than 0. When that works the case, because absolute value by definition is distance from 0, then absolute value of function of x becomes the function of x if f of x is greater than or equal to 0, and it becomes the opposite of that if f of x is less than 0. For the equalities, absolute value of x equals a, x is plus minus a, absolute value of x is less than a is sandwiched between minus a and a, and absolute value of x larger than a, x is less than minus a, or x is larger than a. Here's the graph of an absolute value function. It's a V shape. Domain is all real numbers, but the range goes from 0 to infinity. When we do the transformation, we are assuming c is a positive number. It's easier to deal with it that way. So if y equals f of x plus c shifted up by c units, f of x minus c shifted down by c units. F of x minus c shifted to the right, f of x plus c shifted to the left by c units. And when y equals f of x is given, minus f of x flips it over with respect to the x-axis. F of minus x flips it over with respect to the y-axis. When c is larger than 1, you multiply it by c, the y-coordinate gets larger and it's extended along the x-axis, c times f of x. And if you divide by c, it shrinks by a factor of c. So this is the synopsis of that. And now 1.7 inverse functions, one-to-one functions. The function is one-to-one if each element in the range corresponds to exactly one element in the domain. Example 1. If we look at this A having coordinates 1, 2, 3, 5, 4, 6, minus 2, 1, those are the pairs, and B 1, 2, 3, 5, 4, 6, minus 2, 5. We want to check this. Notice 1, 3, 4, minus 2 are different. So the x coordinates are not being repeated. Excuse me. A is a function. B, 1, 3, 4, minus 2 are not being repeated, the same as this one. And therefore, both of them have the quality that x is not being repeated. Therefore, both A and B represent functions since each x coordinate corresponds to exactly one y coordinate. If you look at part A or set A, 2, 5, 6, 1 are different, so it's also a one-to-one function. Set A is also a one-to-one function since each y coordinate also corresponds to exactly one x coordinate. When we look at part B, 2, 5, 6, 5, notice this repeats. And therefore it fails to be one-to-one. Set B is not a one-to-one function since the y coordinate 5 corresponds to two x coordinates 3 and negative 2. A function f is one-to-one if for any two numbers a and b in its domain, f of a equals f of b results in a being equal to b. But if a is not equal to b, results in f of a not being equal to f of b. Horizontal line test. If a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. So this is clearly a function because it crosses where it passes the VLT, the vertical line test. But it's not a one-to-one function because it fails the horizontal line test. So these 2 points are on the same horizontal line and have the same y coordinate. However, if you cut it half from here, the left hand and the right hand, each one becomes a one-to-one function. Is this a function? Yes. Is this one-to-one? No. If you cut it in half, each half is a one-to-one function too? Yes. Inverse functions. If f of x is a one-to-one function with ordered pairs of the form x comma y, the inverse function, this is read f inverse, not f to the power of -1, f inverse of x is also a one-to-one function with ordered pairs of the form y comma x. So in short, interchanging x and y result in its inverse. So given the function here, 1, 4, 2, 0, 3, 7, -2, 1, -1, 5, find the inverse function. So when a bunch of pairs are given, all you have to do interchange them. So this becomes 4, 1. This one, 0, 2, 7, 3, 1, -2, -5, -1. That would be the inverse. If you plot the pairs 3, 7, and 7, 3, 1, 4, and 4, 1, 0, 2, and 2, 0, and so forth. They are symmetric. Points for the two functions are symmetric with respect to the line y equals x. As we interchange x and y, then they become symmetric with respect to the line y equals x. Inverse functions, find inverse functions. Only one-to-one functions have inverse functions. The domain of f is the range of f inverse. The range of f is the domain of f inverse. The graphs of f and f inverse are symmetric about the line y equals x when graphed on the same set of axes. To find the inverse function of a one-to-one function, replace f of x with y, interchange the two variables x and y, solve the equation for y, replace y with f inverse, the inverse function notation. And again, caution, the negative one in f inverse is not an exponent. It's just straight f inverse. Find the inverse function of f of x equals 4x plus 2 and graph both f of x and f inverse. Number one, we are going to change f of x to y just because it's easier to work with. That's the only reason. Number two, we are going to interchange x and y. So this becomes x, this becomes y. By the way, for this, if we were to graph it, you can see the y-intercept of 0, 2. If I put 1, I get 6. We can also see the x-intercept. If I put a 0 here, just for the sake of argument, if I put 0 here, x becomes negative 1/2. So we have negative 1/2, 0. And so we can plot zero, 2, roughly here, negative 1/2, 0, roughly here, and that's the graph of f of x equals 4x plus 2 or y equals 4x plus 2. So that was the first step. The second step is to interchange x and y. And I want you to know right here, we do have the inverse function. However, we solve for y. So again, I want you to see what happens here. This is the inverse, but we solve for y. Simply put, move the 2, divide by 4. So that's the third step. Call this f inverse. So the third step is to solve for y, and the fourth step is to give it a name f inverse. Now we need a couple of pairs here. You can figure out what the pairs are, or just simply put 0, 2 becomes 2, 0, 1, 6 becomes 6, 1, negative 1/2, 0 becomes 0, negative 1/2. Okay, very simple. So in this case, 2, 0 is here. 0, negative 1/2 is here. Put them together. And symmetric with respect to the line. This is y equals x, everybody. So we graph this function. We found its inverse. We use the same set of axes, and we notice it's symmetric with respect to y equals x. By the way, I hope you can see that this work with this. You can plug in, you see that 2 minus 2 over 4, for example, is here. Here's another function, f of x is 5x minus 2. And f inverse is given as x plus 2. And we want to graph the two on the same set of axes and compare. So let's graph this by plugging two pairs. Clearly, negative 2 is the y-intercept, meaning 0, comma, negative 2. And then if you set this equal to 0, y equal to 0, that means f of x is 0. 5x is 2. X is 2 over 5. So we have those two pairs. So it looks like this. Zero, negative 2. 2/5 is a little bit less than 1/2. So somewhere here. And that's your graph. Now, if I want the inverse, I can use the same pairs and reverse them. So minus 2, 0 and 0, 2/5. So I don't have to even evaluate it. I did the evaluation for the first one. For this one, I just, x and y are interchanged. And so to graph that, we have 1 and 2, negative 2, 0 to the left, 0 and 2/5 somewhere here. And that would be the graph. And symmetric with respect to the line. Y equals x. So the graph of f inverse of x can be drawn by reflecting the graph of f across the line y equals x. That's another way of doing that. Inverse functions. For any one-to-one function, f of x, and its inverse, f inverse of x. F of f inverse of x equals x, f inverse of f of x is x. Their composite function is x. In this case, x is in the domain of f inverse. In this case, x is in the domain of f of x, this second piece, okay? So for example, we want to show that these two functions are inverse functions. So we have to look at f of f inverse and f inverse of f. You don't have to look at both, but we want to do it for practice, okay? As long as one of them is proved, it indicates the two are inverse functions. So let's look at f of f inverse of x, which means replace the x with that. That's the meaning of f of f inverse. Replace the x with f inverse. As you can see, these two cancel each other. We get x minus 2 plus 2, which is x. Let's look at f inverse OF. So that means into this, replace the x with 4x plus 2. And obviously, Positive 2 and negative 2 cancel each other. 4x over 4 equals x. So we proved this one and this one. Verify that f and g are inverses. F of x is 4x minus 3, g of x is x plus 3 over 4. As long as you verify one of them is good enough. For practice, we are going to do both. So we are going to do FOG, okay? We are going to look at the composite function FOG. If it's x, that's a proof. So FOG of x is f of g of x, which means we are going to replace the x with this guy. And we can write f of a g, put the g here. That is actually an interesting step. Mostly I skip that, but you're more than welcome to use it. So now in this case, 4 times this number minus 3, this expression, 4 times x plus 3 over 4 minus 3. These two cancel each other, x plus 3 minus 3, of course. These two cancel each other and 6. That's a proof and we are done. I want you to know that we verify that we are done. But for practice, let's also look at GOF. GOF is G of f of x. That means G of 4x minus 3. That means we're going to put this in here. That's the meaning of it. So we get 4x minus 3 instead of the x, and then we continue with the rest. These two cancel each other. And 4x over 4 is x. And also verified in this fashion. Since f of g of x equals x and g of f of x equals x, f and g are inverses. Find f inverse of x for the function f of x equals 7x minus 4. So, number one, we are going to call this y because it makes life easier. Number two, we are going to interchange x and y. This becomes x, this becomes y. Right here, we have the inverse. However, we solve for y. To solve for y, we move the 4. And we divide by 7. Finally, we call it f inverse of x. So we have found f inverse. Now, we have to verify that. Always it's a good practice. Did we come up with the correct answer? And so we have to use one of these two. And so we are going to look at f inverse of x. And if we come up with x, that verifies it. So that means this will replace the x here. 7, x is replaced by x plus 4 over 7. we get x plus 4 minus 4 equals x. And of course, I don't have to use F inverse OF. One is good enough. You can do that for practice since F of F inverse of x equals x. And I'm going to leave this for you to show, okay? F inverse OF of x equals x, they are inverse. One is good enough, everybody. One is good enough. Again, for practice, I highly recommend you do this part. All right. Sketch the inverse of the function whose graph is shown. We can draw the line y equals x and reflect the graph on the line. So that means one easy way, find a few easy points on the graph of the red function, the f function, and then the corresponding points on its inverse. For example, this point seems to have coordinates -2, comma, -4. So this point is an element. This is how we read this. Looks like an epsilon. -2, comma, -4 is a point that is an element of f of x. By that we mean what? F of -2 equals -4. This means f inverse of -4 must be -2. This means, simply put, interchange these two. -4, comma, -2 is an element of f inverse of x. Now, if you don't want to do that, you don't have to, but I'm just going over more details. So if this point belongs to f, then -4, -2 belongs to its inverse. So that's the point with coordinates -4, -2. Let's pick another easy point. The y-intercept is located at 0, 4. 0, 4 is one point on the graph of f of x. A short version, 4, 0, belongs to f inverse. A long version, this means f of 0 equals 4, and this means f inverse of 4 is 0. But as I said, long versus short. Just go this way and say if 0, 4 is f of belongs to f of x, 4, 0 belongs to its inverse. That's simple, okay? Now, let's locate that 4, 0 is that one. We can pick more and more points. Let's look at another one. This seems to be located at -1, comma 3. If this belongs to f of x, then 3, comma, -1 belongs to its inverse. Short version. Long version, f of -1 is 3. F inverse of 3 is -1. And so, as I said, the short version, 3, comma, -1 is an element of f inverse. Locate that one. The other thing that is extremely important, if inverse functions ever cross, At the point of intersection, their x and y must be identical because the x coordinate becomes y, the y coordinate becomes x for the inverse function. So if they ever intersect, they have to intersect with the line y equals x. So this point, which belongs to the line and the curve, also belongs to the inverse function. And if it's not enough, you can pick more points. So something like this is the graph. Again, if this is not good enough, pick more points, class. But that's how you graph them. You pick easy points from one graph and then corresponding points from the other. We know that, and for this example, we are verifying inverse functions where g of x is x cubed, g inverse is cube root of x. And all you have to do, look at the composite function in any order. So if I look at g inverse of x, that means for x here, I'm going to replace this with cube root of x. And as you can see, they cancel each other and we get x. I don't have to go the second route, but let's quickly do that. G inverse of g of x. That means put this one in here. G inverse of g of x. That means put this one in here. As you can see, cube root of x cubed is also x. So both are easy to verify. Again, you don't have to do both. One is good enough. Part B, f of x is 2x plus 3, f inverse is half of x minus 3. So if we go with f of f inverse, that means replace the x with this. Clearly, this 2 and this 1/2 cancel each other. We have x minus 3 plus 3, which is x. Now, f inverse of, that means, look at f inverse, replace the x with this statement. So half of x becomes 2x plus 3. And then this one remains. And these two cancel each other. Half times 2x is x. That is also a verification, everybody. So we proved in both cases A and B that the two given functions are inverse of each other. Let's look at this example. F of x is given as x cubed plus 1. We want to show that f inverse is cube root of x minus 1. And to show that, all you have to do, look at their composite function, it must be x. So if I look at f of f inverse, that means f of f inverse of x, that means f of cube root of x minus 1. That is by definition. So I'm going to replace the x here with this function. And of course, cube root of x minus 1 being raised to the power of 3, they cancel each other, give us x minus 1. With this plus 1 becomes x. And again, we are done, everybody. But for practice, let's look at f inverse of, which means now this is f inverse of f of x, which means this will replace the x here. And so put this in here. These two cancel each other. We get cube root of x cubed, which is x. All right, let's look at this example. Given f of x equals square root of x plus 5, f inverse is x squared minus 5 when x is larger than or equal to 0, show that the above is true. So f of f inverse of x means you will replace the x with x squared minus 5. These two cancel each other. You get square root of x squared and it's equal to x. Please pay attention to the fact that this says x is larger than or equal to 0. Otherwise, square root of x squared is absolute value of x, okay? And so the reverse, the second one, you don't have to do, but we want to verify that f inverse of f of x, that means go to this function and replace the x with square root of x plus 5. This is simple. When you square this, square root just comes out, becomes x plus 5. And these two cancel each other. The answer is x. Now let f of x be cube root of x plus 10. We want to find f inverse and show that the above is true. So number 1, we're going to call this y to make it easy to work with. Number 2, we interchange x and y. And right here, we have the inverse. However, we solve for y. We're going to move the 1 and we're going to raise both sides to the 3rd power. So x minus 1 cubed is y. Let me just change this to 10. I meant to put 10. So this is 10, everybody. Okay. And so give it a name f inverse and you're done. But to verify the above, we are going to do one of them. If I want to look at f of f inverse, I'm going to replace this x with the expression x minus 10 quantity cubed. X minus 10 quantity cubed, the cube root of that comes out as x minus 10, and x minus 10 plus 10 give us x, and we are done.